Good morning and welcome to this next lecture on vibrations of plates and shells. We were deriving the condition for orthogonality of modes, and we were at this point. The Hamilton's law without the boundary and loading terms looks like this, and the variation of the strain energy and kinetic energy have this form. Now we said that we will represent the displacement as the mode shapes. Okay. So ui, where I can stand for 1, 2 or 3, 1 in the alpha 1, 2 in the alpha 2, 3 in the alpha 3 directions. So we will have this form, okay, and u1, u2, u3 will be in one mode. Okay, all three displacements represented by one mode. So u1 alpha 1 alpha 2 will be u1k, u2 will be u2k, and u3 will be u3k. So this, I told you, this whole thing is one mode shape, the kth mode shape, and it vibrates at one single frequency. Similarly, when there is a variation, when there is a delta 1 or a delta u2 or a delta u3, they will be represented in the alpha, I mean u1p, u2p and u3p components of the pth mode shape. Why? Because the variation should satisfy the boundary conditions, cannot violate the boundary conditions, it also satisfies the boundary conditions. Okay. And so we will represent the variations as another set of mode shapes. Okay. So as a result, what do we see happening? What we will see is this: the Hamilton's law will acquire integral T1 to T2, integral alpha 1, integral alpha 2, integral alpha 3, sigma 1 1 k, okay, and delta epsilon 1 1 p, plus sigma 2 2 k, delta epsilon 2 2 p, plus sigma 1 2 k, delta epsilon 1 2 p, plus sigma 1 3 k, delta epsilon 1 3 p, plus sigma 2 3 k, delta epsilon 2 3 p. A1, A2, d alpha 1, d alpha 2, d alpha 3 dt. Okay. And that on the other side is going to equal omega k square rho h integral T1 to T2 integral alpha 1 integral alpha 2 u1k u1p plus u2k u2p plus u3k u3p. A1, A2, d alpha 1, d alpha 2 dt. Okay. So what did we do here? Here u1 double dot, okay, acquired the minus omega k square, and minus became plus, whereas for the delta u1, delta u2, delta u3 we use the pth mode shape. Okay. Of course these will be there, e to the power j omega kt, and temporal terms will be there. So you will get omega k plus omega p times t, and e to the power j omega k plus omega p times t, okay, and nowhere else there is time. So, this time integral will get eliminated from both sides. Okay. So, we will deal with only the spatial integrals. So, now if we look at, for example, a term like this, if we look at a term like this, okay, let me give you the idea first. Okay. So, the idea is on the right hand side, we are going to switch k with p and p with k, we are going to switch. So, the right hand side looks like omega p square rho h. I will keep the time out. Again u1p u1k plus u2p u2k plus u3p u3k, a1 a2 d alpha 1 d alpha 2, and we are going to subtract, and so on the right side we get omega square k minus omega square p into rho h integral alpha 1 integral alpha 2 u1p u1k u2p u2k plus u3p u3k a1 a2 d alpha 1 d alpha 2. That is what we get. Now, if we can show that the left side is 0, which we will do in a while, okay. If we show on the left side the term is 0, that means when we switch k to p in this term also and we subtract, okay, then what happens is when k is equal to p, okay, then we get anyway the right hand side is 0. Okay. However, when k is not equal to p, then also the right hand side is 0, okay, because that is what the left side is saying. Okay. Then in such a case what we have is integral alpha 1 alpha 2 u1p u1p u1k is not equal to p plus u2p u2k plus u3p u3k a1 a2 d alpha 1 d alpha 2 must be 0. So, this is the orthogonality. Okay. When p and k are not equal, then the orthogonality of the mode shape is given by this condition. Okay. So, that is the idea. So, now we have to work on this term here. Okay. Now, let me show you what happens with sigma 1 to k delta epsilon 1 to p. Okay. Sigma 1 to k delta epsilon 1 to p. Now, let us see. Epsilon 1 2 is equal to a1 by a2 del del alpha 2 u1 by a1 plus a2 by a1 del del alpha 1 u2 by a2, and hence delta epsilon 1 2 is given by a1 by a2 del del alpha 2 delta u1 by a1 plus a2 by a1 del del alpha 1 delta u2 by a2. And sigma 1 2 is g epsilon 1 2, and therefore g times a1 by a2 del del alpha 2, etc. Okay. And so sigma 1 2 delta epsilon 1 2 is given by g a1 by a2 del del alpha 2 u1 by a1 plus a2 by a1 del del alpha 1 u2 by a2 into a1 by a2 del del alpha 2 delta u1 by a1 plus a2 by a1 del del alpha 1 delta u2 by a2. Now what I propose is that wherever we have u1, it is the u1 mth mode, the mth natural frequency. Wherever you have u2, it is the u2 component of the mth natural frequency. Whereas if I have delta u1, then it's u1 component of the nth natural frequency n. Similarly, delta u2 is the u2 component of the same nth natural frequency. Why? Because variation satisfies the boundary conditions, and so does the mode shape. Okay. So if we do that over here, I get sigma 1 2 delta epsilon 1 2 k and p, or what did we do? Yeah, we said k and p. Okay, sorry, we'll do that, k and p. So this will be k and this will be p. P. So this now becomes equal to g a1 by a2 del del alpha 2 u1p by a1 plus a2 by a1 del del alpha 1 u2p by a2 into a1 by a2 del del alpha 2 delta U1 is U1P. So this is U, how come again, sorry. This is K, this is K, okay. This is P by A1 plus A2 by A1 del alpha 1 U2P by A2. Okay. So if we switch K to P, P to K, if we do sigma 1 to P, delta epsilon 1 to K, okay, then what happens? G A1 by A2 del alpha 2 U1P by A1 plus A2 by A1 del alpha 1 U2P by A2 into A1 by A2 del alpha 2 U1K by A1 plus A2 by A1 del alpha 1 U2K by A2. So you can see you have U1, this term and this term all same except U1K, U1P is the same as this term, this product over here. Okay. Similarly U2K, U2P product over here del alpha 1 is U2P, UTK product over here. So there are same, the terms are same. So if I subtract, I get a 0 at least with respect to the shear terms. Okay. So if I do a subtraction, if I replace K with P and P with K and do a subtraction, the shear terms will vanish. Okay. Now let's see what happens to these terms. Okay, what happens to those terms? So let's see. So let us first write down epsilon 1 is equal to 1 by E sigma 1 sigma 1 minus mu sigma 2 and epsilon 2 is equal to 1 over E sigma 2 minus mu sigma 1. And sigma 1 is E over 1 minus mu squared epsilon 1 plus mu epsilon 2 sigma 2 is equal to E over 1 minus mu square epsilon 2 plus mu epsilon 1. And what is epsilon 1? Epsilon 1 is 1 over A1 del alpha 1 U1 plus 1 over A1 A2 del alpha 2 of A1 into U2 plus U3 by R1, and epsilon 2 is equal to 1 by A2 del alpha 2 of U2 plus 1 by A1 A2 del A2 by del alpha 1 U1 plus U3 by R2. Okay. So if we now do sigma 11 k delta epsilon 11 p, we do that, then we get E over 1 minus mu squared epsilon 11 k plus mu epsilon 22 k delta epsilon 11 p, which I'll take it from here, E by 1 minus mu square 1 by A1 del alpha 1 U1 k plus 1 over A1 A2 del A1 by del alpha 2 U2 k plus U3 k by R1 plus mu 1 by A2 del alpha 2 U2 k plus 1 by A1 A2 del A2 by del alpha 1 U1 k plus U3 k by R2. Into 1 by A1 del U1 p by del alpha 1 plus 1 by A1 A2 del A1 by del alpha 2 U2 p plus U3 p by R1. Okay. Similarly, sigma to 2k delta epsilon to 2p results in E over 1 minus mu squared 1 by A2 del U2 k by del alpha 2 plus 1 by A1 A2 del A2 by del alpha 1 U1 k plus U3 k by R2 plus mu times 1 by A1 del U1 k by del alpha 1 plus 1 by A1 A2 del A1 by del alpha 2 U2 k plus U3 k by R1 multiplied by 1 by A2 del alpha 2 U2 p plus 1 by A1 A2 del A2 by del alpha 1 u1 p plus u3 p by r2. Okay. So now what do we have? Let's see if we have this term, okay, with a u1k, we have this term with u1p. They will go in a product, okay. Then we have this term with a u2k, okay, this term with a u2k, and this term with a u2p. They will also go in a product. Okay. Similarly, we have this term and we have this term. Okay. Then what do we have? Then we have a term. I'm just looking for some of the terms. Okay. So I have 1 over a1 a2 del a1 by del alpha 2 u2k into 1 over a1 del u1p by del alpha 1. Okay. If we look at these two terms here, let us see. If we look at these two terms here, I again get 1 over a1 a2 del a1 by del alpha 2 u2p 1 over a1 del by del alpha 1 u1k. Okay. So these are the two terms. Okay. So now if I change k to p and p to k, okay, if I change k to p, this will become a p and this will become a k. Okay, then it's the same term as before. Okay, these two are summed up. Similarly, if I change this to k and this to p, then also the term is the same. Okay. So with these two terms, sigma 11k delta epsilon 11p plus sigma 22k delta epsilon 22p, you'll get one set of terms. And if I change k to p, sigma 11p delta epsilon 11k plus sigma 22p delta epsilon 11k, I will get the same set of terms, same terms. Okay. So as I said before, when we subtract k with p replaced, p with k replaced, and then subtract, then the left side will be 0 and the right side will look like this. Now if k is equal to p, then of course this term goes to 0. However, if k is not equal to p, still the term has to go to 0, RHS, and then you get a orthogonality condition on the mode shape. Okay. So as I said before, U1p, U2p, U3p together is the pth mode shape. Similarly, U1k, U2k and U3k together, they form the kth mode shape. And so this is the orthogonality condition, okay, for a general shell. Okay. Now it will turn out that if you take flat structures like plates and so forth, then the transverse motion of the plate is uncoupled from the in plane motion. Okay. In that case, the orthogonality purely becomes U3p U3k integrated over alpha 1 alpha 2 is 0, provided p is not equal to k. A1 A2 d alpha 1 d alpha 2. Okay, because the in plane motion is now decoupled because of infinite radii of curvature. Okay, so that is the most general orthogonality condition for a curved shell. We will use this later. Okay. Now, with this, I complete the portion of mode shapes and natural frequencies. In which the modes are analytical formulas, Okay. However, it is not always possible, to find mode shapes analytically. That means as a closed form formula, okay, like some sine m pi x by L cos n theta, like that. It is not always possible. Okay. And then you have to resort to some approximate method, some numerical scheme. You have to resort to some approximate numerical method. Okay. So in that league will come this method called Rayleigh quotient and Rayleigh-Ritz. Okay. So now the Rayleigh quotient and the Rayleigh-Ritz method, they depend on the idea that when there is no damping, the system is conserved, system is conservative. And it is in vibration, free vibration, then its maximum potential energy is equal to the maximum kinetic energy. Okay. So now if we adopt this idea that the maximum potential energy is equal to maximum kinetic energy, this idea is used in the Rayleigh quotient. In finding the fundamental resonance frequency, finding the fundamental resonance frequency. We must have seen this before in single degree of freedom systems. Okay. If I have, let us say, a spring mass system and it is freely oscillating, let this be m, let this be k, then the kinetic energy is 1/2 mx dot square and the potential energy is 1/2 kx square. Okay. And let us say x, the displacement is some a sine omega nt, then x dot is equal to a omega n cos omega nt. Okay. So that the kinetic energy is given by 1/2 m a square omega n square cos square omega nt. Okay. And the potential energy is given by 1/2 k a square sine square omega nt. Okay. And the maximum value of this, maximum value is 1/2 m a square omega n square and the maximum value is 1/2 k a square. Okay. So if we equate the two, 1/2 m a square omega n square is equal to 1/2 k a square, or rather omega n square is equal to 1/2 k a square, the maximum potential energy. Okay. V is the symbol for potential energy, and then 1/2 m a square. This is the kinetic energy function. It is not the full kinetic energy because omega n square is left here, but this is the kinetic energy function. We will call this the psi m. And so omega n square is equal to the Vm by psi m, and this is called the Rayleigh quotient. Rayleigh quotient. Rayleigh quotient. And so the Rayleigh quotient gives the estimate of the fundamental frequency of the system. Okay. We can take a higher order system, we can take a next level system. By the way, I will tell you the textbook I am taking this portion from. I will tell you in the next class. Okay. So this okay. So now what next? So I said Rayleigh quotient, okay, gives the estimate of the fundamental natural frequency. So let us say I take now a higher order system. I take a higher order system. This is 0.2 kg. This is 0.3 kg. Okay, I think we are running out of time. I'll stop here and continue from the next class from this point. Thank you.